I'd like to go over this problem 12.26 because it's a difficult problem and it involves several of the concepts that I think are important for you to understand in chapter 12. In the problem, we have a 1.0 kilogram ball and a 2.0 kilogram ball connected by a 0.80 meter long rigid massless rod. The rod is rotating clockwise about its center of mass at 18 revolutions per minute. What torque will bring the balls to a halt in 6.0 seconds? So I've drawn a figure of the rigid rod with the masses on each end. I have the small mass on the left and the large mass on the right. And I indicate that the length of the rod is L, and the small mass is located at distance x1 from the center of mass, and the larger mass at x2 from the center of mass. We're asked to find the torque. And Newton's second law for rotational dynamics is torque is equal to the moment of inertia times the angular acceleration. So we're going to have to determine what the moment of inertia is and what the angular acceleration is to work this problem. Well, the moment of inertia for this system is equal to the small mass times x1 squared plus the larger mass times x2 squared. Those are the contributions to the moment of inertia of this system from each end of the rod. And we don't worry about the rod itself because they tell us it's massless. Okay, so now we need to determine what x1 and x2 are in terms of L. And to do this, we employ our definition of center of mass. And we'll make our determinations simple by asking what is the center of mass of the system with respect to the left-hand mass. Look, so we have at a distance L from the left-hand mass, the big mass, and we want to find out what the location of the center of mass is, which in this case is equal to x1. So x1 then is equal to, by our definition of center mass, equal to big M times L over the sum of the masses, big M plus little m. Big M is 2, little m is 1, so this tells us that x1 is equal to 2/3 L. And that must mean that x2 is equal to L minus x1, which is equal to 1/3 L. Okay, so now we can go back to our determination of the moment of inertia. I is equal to the smaller mass, which is 1, times x1, which is 2/3 L all squared, plus big M, which is 2 kilograms, times 1/3 L all squared. So then this is equal to 4/9 L squared plus 2/9 L squared. That's 6/9 or 2/3 L squared. Okay, where it's understood that kilograms are in the units here. And L is going to be in meters. All right, so now we've determined what the moment of inertia is for this system. Next, we need to find out what the angular acceleration is. Well, we have the angular analog to our equation number 1 from our kinematics equations with constant acceleration. In this case, we have constant angular acceleration. And the final angular velocity is equal to the initial angular velocity. Excuse me, that shouldn't be squared. Is equal to the initial angular velocity plus alpha t. And this is coming to rest, so the final angular velocity is 0. And omega is equal to minus alpha t. So that tells us that alpha is equal to minus omega naught over t. All right. Now, omega naught is equal to 18 RPM, and t is equal to 6.0 seconds. But this angular velocity is clockwise, and that's a negative. If it's clockwise, the sign of that angular velocity is negative. So we're going to have a negative times a negative and when we calculate alpha here. So we'll write this as 0.80 excuse me, not 80, 18 revolutions per minute divided by 60 seconds, 6.0 seconds. And we have, for every revolution, we have 2 pi radians. And for every minute, we have 60 seconds. And when I calculate that, I get pi over 10 radians per second squared for alpha. So I'll let you finish the problem. The torque is given by I, which we said is 2/3 L squared times pi over 10 radians per second squared, where L is in meters, and there's also kilograms in the units. Your result will be in Newton meters. And that concludes this video.